started, I was encouraged to do that before people decided to go someplace else. So it's a pleasure to be here. My name's Todd Anderson. I'm representing PHINIA, and I'm excited to talk about some end use for what our conference is about for hydrogen and how we can use that to move toward decarbonization. Before I start, do we have any admitted gearheads in the audience? Folks who have lived and worked around cars and engines. So I'm talking to you. Do I have any who really don't work with engines or cars? I'm talking to you as well, because this combines hydrogen supply, hydrogen opportunity, with end use in the transport market. So I'll be talking about how we empower this transition in the transport market toward carbon neutrality. Let me do a brief introduction for PHINIA. This is a new name, but we've been around for over 100 years. You may have known us previously as Delphi or Delphi Technologies, recently with Borg Warner. PHINIA became a company in July of this year, spun out separately. We're a roughly $3.5 billion global business, Tier 1 automotive supplier, and we have, as shown here, 44 locations in 20 countries, around 13,000 employees. So what does PHINIA do? Our history and our experience is providing leading integrated fuel systems and components. This would include fuel injectors, common pressure rails, fuel pumps. Importantly, and I'll talk more about this, the software, system integration, engine control units, and calibration required to bring all those together into a working engine and a working vehicle. We provide fuel delivery modules and canisters. I share that to share our experience positions us strongly to be able to take this competency and move it forward into a hydrogen platform to be able to leverage existing infrastructure, skills, and capabilities in order to advance us toward carbon neutrality. So to achieve our global CO2 reduction goals, we believe it's going to take all technologies to do that. We're not a one answer, we're not in a one answer problem. And those technologies will be used where they're best suited and in the best applications. But as we leverage all of those, we'll be able to move forward most rapidly and most effectively. We see here on the left that there are multiple paths toward decarbonization. This includes e-fuels with an internal combustion engine, could be hydrogen ICE, which I'll talk more about, fuel cell technology we've heard about today with hydrogen, even battery electric vehicles, all can play a part in our goal to reduce carbon. On the right side, you see some of the benefits where hydrogen ICE, an internal combustion engine, displays distinct benefits in the transport market. This includes using a fuel that starts out with zero carbon, rapid and easily accessible refueling, low weight, as well as using existing materials, supply chain, manufacturing footprint, and infrastructure. So with H2 ICE, we see a strong, viable path forward toward relatively rapid implementation opportunities. Well, what does that look like? For a vehicle to run with a hydrogen internal combustion engine, it would of course have a supply tank for the fuel, in this case gaseous hydrogen. It has hydrogen regulation and distribution components, and then it will inject that into a combustion engine. This is showing a picture of our direct inject compressed hydrogen gas injector. Importantly, the control system to do this will control not just engine parameters, but injection parameters, and calibrated appropriately can result in an engine that delivers similar power density and performance to what we experience with diesel engines, only without the carbon emissions. So to make this happen and convert a vehicle, which we have done and I'll talk more about, to a carbon neutral H2 ICE, it requires us to address several key elements of that system. Some of those are listed here: the fuel injection system, engine modifications, which frankly are fairly minor when it comes to taking an existing diesel or gas engine and being able to convert that to run with a hydrogen fuel. Engine controls, the hydrogen storage and supply are required, and then we do utilize an exhaust aftertreatment and SCR system, and I'll talk more about that as I share in our emission results that we've seen in both lab testing and test protocols in real-world driving. I wanted to go over this because we started, as you might expect, with a demonstrator and then moved to an engine and then continued our learning as we incorporated that into a vehicle. And we learn all the way through that process in this project of bringing this to light. One of the areas that we've done significant work is related to the control functions. I like to hold parts and to look at them. I'm passionate about the components that we make, and frankly, I could talk for hours about the injector itself and how we have micron clearances and millisecond actuation in these injectors. They're incredible devices. But all of that becomes an expensive paperweight if you don't have the right control systems and system integration and calibration to make it work in the vehicle. In this case, we started out on the left-hand side. You can see a typical base controller system for a light commercial vehicle, a van. As we went to convert this to an H2 ICE, we added a dual controller, a generic H2 controller that acts in partnership with the vehicle controller. Now, in a production scenario where we go to high volume, this could be optimized, of course, into one control unit. But what this strategy allowed us to do is to move quickly and robustly with strong performance toward actual operation of a vehicle. We're all about practicality, and let's be pragmatic as we move forward, take steps now that we can take now in order to improve in carbon emissions. We heard this morning a lot about partnership, and it's a core foundation for us at PHINIA. So this project was the result of partnership and collaboration with some experienced and skilled industry partners. And we continue to look for opportunities to partner in our global collaborative quest to improve decarbonization. In the center, you see the project targets that we started out with in making this vehicle conversion. And as noted with the green checks, which represent we did it, we were able to successfully achieve those targets. On the far right, you see an example of one of the vans that we have operating on the roads in Europe. Thousands of kilometers that have been logged, thousands of passengers, industry, government officials that have been able to experience this progress in technology. I mentioned down below that we're certified to operate on public roads in Europe at a prototype level. We continue to take steps towards certification as a production vehicle. So let's talk a little bit about the data. That's great, and we see it on slides, but what does the data show us? In the worldwide harmonized light vehicle test procedure on the left-hand side, we went through this procedure And what I'm showing on this chart are NOx emission results. So the proposed Euro 7 legislation will be, for lighter vehicle, will be 60 milligram per kilometer, or maybe for a little bit heavier vehicles up to 75 milligram per kilometer. As we went through this standard test procedure, we experienced a NOx tailpipe out of 10 milligrams per kilometer. So maybe actually let me add an orientation point. This black line is our engine out NOx that you can see over the test procedure. The red line at the bottom is our tailpipe out NOx, which is comfortably below even future proposed emission requirements. Then when we take this vehicle on the road and use it in a real driving condition under heavy loads, we are able to experience and measure a tailpipe out NOx of 4 milligrams per kilometer. So negligible NOx, comfortably meeting even proposed future emission standards with this vehicle and this H2 ICE engine. Well, NOx isn't the only thing that we care about. So let's look at our test results with other gaseous pollutants. Here we see the proposed targets for carbon monoxide, for hydrocarbons, for ammonia, and we see the results of our H2 ICE. Or maybe I could say you might be able to see those. They're way down at the bottom. Actually, we have very good results with these other gaseous pollutants. And CO2 was measured below 10% of atmospheric background, less than 0.5 grams per kilometer. So it's fine to do that with proof of concept or a prototype that gets shepherded and carefully followed through a build process. But for us, that's not sufficient. For us to make this work and to contribute to our global decarbonization goals, it needs to be done in volume. And we need to be able to produce it reliably by the tens and then hundreds of thousands, time and time and time again. That's where PHINIA's background shines, in reliable, consistent, high-volume manufacturing. And we've begun that process with components for our hydrogen ICE using an injector pilot line at our facility, showing stable flow curves, very low part-to-part variation, and in our engine durability testing have consistent and well-defined static flow drift, well within specification, as well as tip leak. So these are parts that we can make at volume, we can make reliably, and can contribute now today toward decarbonization. So this is my last slide, and I'd like to conclude with a few encouraging words and actually a call to action. So my claim that I'm here representing is hydrogen ICE technology is ready. It's available. It utilizes existing infrastructure in very positive and constructive ways. And it helps us be able to accelerate our steps toward decarbonization. Hydrogen ICE can have a positive impact now on our global path toward carbon neutrality. But to do that, this call to action at the bottom, we need what we've been talking about this whole conference. So we're here to be able to provide demand, end-use demand, and a place where hydrogen produced by renewable sources can be used in the transport industry to be able to move us along our goals. To do that, we need to make sure that the infrastructure is in place. In Europe, they have the alternative fuel infrastructure regulations that are helping. We've heard a lot this morning about that taking place in North America as well. So I'm really excited to be here and to partner with you and with the industry to help us move forward. Thank you very much. It shows I have 2 minutes here. So yes, please, a question?
Yeah, thank you so much for your presentation. Can you comment on the TCO comparison with the hydrogen ICE and the diesel ICE, and how much the vehicle cost factors into that?
Okay, did I hear ECU?
No, TCO.
Oh, TCO.
TCO. Yeah.
TCO can be comparable, but it depends on volume, of course. And as I mentioned, some of the work that we have done here is not optimized for higher volume. But at volume, when we look at the components of the system, we anticipate that TCO will be very similar to what we would experience today.
What volume do you think that this will be comparable?
Well, let me share that. I don't have that in my head directly, but let me share this. We make fuel injection systems for 4 to 5 million vehicles. And so I believe as we start out, there will be a gradient there. We have an initial start of production that begins in 2024 for an off-road vehicle application, and we continue to work. We have additional work going on. I would say that we'd start to see some benefits in volume around the 70 to 100,000 range, but of course that's going to be a sliding scale. Thank you. Any other questions? Yeah, here's a, yeah, please.
Yeah, so on the NOx emissions, I guess maybe I didn't quite understand the slide, but were you saying that the NOx levels stayed within regulation, but how did they compare when you were burning gasoline or diesel?
The NOx levels are much lower than when we burn gas and diesel, but the gas and diesel that's happening now is going through the similar type of emission controls to meet Euro 7 regulation. So I would, to say it simply, the H2 is below that of what we experience with gas and diesel.
Thank you.
Yeah. And one here?
Within North America, where do you see the most, the lowest hanging fruit for the market for this technology?
Thank you. Great question. We see this being really well suited for applications that are high load, continuous use, heavy duty cycle. So long haul trucking, for example, would be a great application for this because of its power density, its performance requirements. As we start out, based on infrastructure availability, we might see captive fleets that are that heavier load, higher duty cycle. That would be low-hanging fruit for these types of opportunities. It can also be expanded into industrial applications, and we're working closely with companies for stationary power generation that have similar needs, continuous, long operating duty cycle, a need for consistent, robust, and reliable performance hour after hour, kilometer after kilometer, year after year. Those are where this technology will really shine. Thank you. Good question. I think my time is up. Thank you very much. I appreciate being here.